If you bought a graphics card in the last 2 years and it came with 8GB of video memory, I have some uncomfortable news for you. That number, which felt perfectly reasonable not long ago, is aging faster than almost anyone in the industry predicted. Cards that were marketed as capable 1080p and even 1440p performers are now stuttering, crashing, or being forced into settings menus to dial back textures just to stay playable. This is not a fringe complaint from a handful of unlucky gamers. It is becoming a pattern, and today we are going to walk through exactly why it is happening, how fast it accelerated, and what it means for anyone shopping for a GPU right now. Let's start with some context, because 8GB was not always a problem. Go back to 2016 when the GTX 1070 launched with 8GB of GDDR5, and that amount of memory was considered generous. Games at the time rarely pushed past 4 or 5GB, even at higher resolutions. Fast forward to 2018 and 2019, and 8GB was still comfortably ahead of what most titles demanded. It became the default expectation for a solid mid-range card. The number manufacturers kept building around because it worked, it was affordable, and it satisfied the vast majority of players. For years, this assumption held up. Cards like the RTX 2070, the RTX 3070, and later the RTX 4060 Ti all shipped with 8GB, treating it as a safe, proven configuration rather than a limitation. The trouble is that game development did not stand still while GPU makers kept recycling that same memory figure. Textures got dramatically larger as displays moved toward 1440p and 4K becoming mainstream targets rather than niche enthusiast setups. Open-world games ballooned in scope, loading in more assets, more detailed environments, and higher resolution character models than ever before. Then ray tracing entered the picture, and ray tracing does not just tax your GPU's compute cores, it also demands additional memory to store acceleration structures, denoising buffers, and lighting data. Add in the rise of frame generation technologies, which need their own memory overhead to store motion vectors and interpolated frame data, and you can see how the walls started closing in on that once comfortable 8GB ceiling. Consider a modern release like Alan Wake 2. At 1440p with ray tracing enabled, it can push VRAM usage well beyond 10GB, sometimes closer to 12GB depending on texture settings. Hogwarts Legacy became something of a cautionary tale on launch, with players on 8GB cards reporting texture, pop-in, stuttering, and outright crashes at settings the card should have theoretically handled based on its raw compute power. The Last of Us, Part 1 on PC, especially in its early patches, was notorious for VRAM-related issues that had nothing to do with a card's shader performance and everything to do with running out of memory headroom. Resident Evil 4's remake, Forspoken, and even older titles patched with high-resolution texture packs have shown the same symptoms. These are not obscure edge cases. These are some of the most played, most benchmarked games of the last few years, and they all tell the same story. Memory capacity, not raw horsepower, is becoming the bottleneck. What makes this especially frustrating is that it creates a strange situation where a GPU has plenty of computational power left in the tank, but it simply cannot hold the data it needs to use that power. Imagine a highly capable chef with a fully stocked set of knives and burners, but a refrigerator too small to store the ingredients for the meal they are trying to cook. The talent and the tools are there, but the storage constraint forces compromises no matter how skilled the chef is. That is essentially what is happening inside these 8GB cards. The GPU core itself, in cards like the RTX 4060 Ti or the RTX 3070, is often perfectly capable of running a game smoothly. But when VRAM fills up, the system has to start swapping data in and out from slower system memory over the PCIe bus, and that swapping introduces stutters, frame time spikes, and in worse cases, outright crashes to desktop. So why do manufacturers keep releasing cards with 8GB when the pattern of trouble is now so well documented? The honest answer involves a mix of cost control and market segmentation. GDDR6 and GDDR6 memory chips are not free, and doubling capacity from 8GB to 16GB adds real cost to the bill of materials. On a budget or mid-range card, that additional cost either eats into profit margins or forces the price up, and price is often the single biggest factor influencing purchase decisions in that segment. There is also a segmentation strategy at play. By keeping certain tiers capped at 8GB, manufacturers create a clear incentive to upgrade to higher tier cards if you want more memory, even if the core GPU performance difference between tiers is smaller than the price gap suggests. It is a business decision as much as an engineering one, and it means the limitation is not accidental. It is, in many cases, intentional. There is also a technical wrinkle worth understanding: memory bus width. The width of a GPU's memory bus determines how many memory chips can be attached and in what configurations. A card with a 128-bit bus, for example, is naturally constrained in how it can scale memory capacity without using more expensive and complex chip configurations. This is part of why some 8GB cards cannot simply be upgraded to 16GB without a fundamental redesign of the board. The memory capacity is not just a marketing choice bolted on top of an otherwise flexible design. In many cases, it is baked into the physical architecture of the card from the very beginning, which makes the decision to ship with 8GB even more consequential and harder to reverse later with a simple firmware update or driver patch. Now let's talk about the acceleration part of this story, because the pace at which this problem has intensified is the real headline. If you had asked someone in 2020 whether 8GB would still be broadly sufficient in 2024, most industry voices would have said yes, comfortably. Instead, what we have seen is memory requirements creeping up far faster than expected, driven by a perfect storm of factors arriving almost simultaneously. Next-generation console hardware pushed baseline expectations higher, since both the PlayStation 5 and Xbox Series X shipped with far more unified memory than their predecessors. And PC ports, built to match those console targets, naturally inherited higher memory footprints. Meanwhile, ray tracing went from a niche toggle and a handful of showcase titles to a mainstream feature expected in most major releases. Upscaling and frame generation technologies, ironically designed to help lower-end hardware perform better, actually add their own memory overhead, partially offsetting the benefit they were meant to provide for cards already constrained on capacity. Texture streaming systems have also evolved in ways that assume more available memory. Modern engines increasingly rely on aggressive texture streaming to load high-resolution assets just in time, but this approach still requires a baseline pool of fast accessible memory to work smoothly. When that pool is too small, the streaming system either has to drop to lower resolution textures on the fly, causing visible pop-in, or it has to wait for data to be fetched from slower storage, causing stutter. Neither outcome is good, and both are increasingly common on 8GB cards running modern titles at anything beyond the most conservative settings. There is also a psychological and cultural shift happening among gamers and reviewers that is worth mentioning. A few years ago, benchmark culture was overwhelmingly focused on average frame rates and raw performance charts. Today, frame time consistency, stutter analysis, and 1% low measurements have become central to how hardware is evaluated. This shift in reviewing methodology has exposed VRAM limitations that used to be hidden or dismissed as measurement noise. Reviewers now specifically test scenarios designed to stress memory capacity, and the results consistently show 8GB cards falling behind their 12GB and 16GB counterparts in ways that pure shader benchmarks would never reveal. In other words, the problem was likely there all along in certain scenarios, but it is only now being measured and reported with the rigor it deserves, which makes the decline of 8GB feel sudden even though the underlying pressure had been building for years. Let's get specific about what this actually looks like in practice, because abstract discussion of memory bandwidth and streaming systems can feel disconnected from the real experience of sitting down to play a game. On an 8GB card at 1440p, with ray tracing enabled in a demanding title, you might see frame rates that look perfectly respectable on paper, sitting somewhere in the 60 to 70 frames per second range according to an average frame rate counter. But then you notice periodic hitches, moments where the game briefly freezes for a fraction of a second as new texture data gets forced into memory, overwriting something that was needed just a moment before. Textures on distant objects or newly loaded areas appear blurry or low resolution for a second or two before snapping into focus. In the worst cases, the game crashes entirely, sometimes with an out-of-memory error, sometimes with no error at all, just a sudden return to the desktop. None of these symptoms show up clearly in a simple average frame rate number, which is exactly why this problem went somewhat under the radar for as long as it did. Compare that to a card with 12GB or 16GB running the same settings, and the difference is often night and day, not because the underlying GPU core is dramatically more powerful, but because it never has to compromise on what data it keeps readily available. The RTX 4060 Ti actually makes this comparison unusually clean because NVIDIA released both an 8GB and a 16GB version built around essentially the same GPU core. Benchmarks comparing the two show nearly identical performance in less demanding titles, but a widening gap in memory-intensive scenarios, with the 16GB version pulling ahead, specifically in situations where the 8GB version starts running into its ceiling. This is about as close to a controlled experiment as consumers are going to get, and the results have been treated by much of the enthusiast community as fairly damning evidence for the 8GB standard. Beyond NVIDIA's lineup, AMD has faced similar scrutiny, though its approach has differed slightly. Several AMD cards in the mid-range segment have shipped with 8GB as well, and while AMD's memory bus configurations sometimes provide a bit more bandwidth headroom, the fundamental capacity ceiling still applies once a game's asset footprint exceeds what 8GB can hold. Reviewers running the same VRAM stress tests across both red and green branded cards have found that the symptoms are strikingly consistent regardless of manufacturer, which reinforces the idea that this is an industry-wide capacity issue rather than something tied to one company's architecture or driver philosophy. It is not a competitive advantage either brand can claim over the other in any meaningful way. It is also worth addressing resolution specifically because a common piece of advice has been that 8GB is fine as long as you stick to 1080p. There was truth to that for a while, but even this fallback position is eroding. Some 1080p configurations in newer titles, particularly with ray tracing or high-resolution texture packs enabled, are now bumping up against 8GB limits. The safety margin that 1080p once provided is shrinking, and it is reasonable to expect that margin to continue shrinking as textures and lighting systems keep growing in complexity. This does not mean every 1080p game requires more than 8GB today, but it does mean the exceptions are multiplying faster than expected. And buying an 8GB card as a long-term 1080p solution is a riskier bet than it would have been just a couple of years ago. So what should you actually do with this information if you are in the market for a new graphics card? The most practical guidance right now is to treat 8GB as a genuine minimum only for lighter workloads and budget builds, not as a safe middle ground choice. If your budget allows it, stepping up to a 12GB or 16GB card provides meaningfully more headroom against the trend we have just walked through. And that headroom translates directly into a longer useful lifespan before you start seeing the stutter and texture pop-in symptoms described earlier. This is particularly true if you play at 1440p or higher, if you care about ray tracing, or if you tend to keep hardware for 4 or 5 years rather than upgrading every generation. For pure 1080p gaming on a tight budget, 8GB can still get the job done today, but go in with clear eyes about the fact that its comfortable margin is shrinking and will likely continue to do so. It is also worth paying attention to how manufacturers position their lineups going forward, because there are signs the industry itself recognizes this shift. Higher-end cards have generally moved to 12GB, 16GB or more, and there has been growing pressure, both from reviewers and from vocal segments of the community, pushing back against new 8GB releases at price points that used to be considered acceptable for that capacity. Whether that pressure translates into meaningfully different product decisions in the next generation of cards remains to be seen, but the conversation itself signals that 8GB is no longer treated as an uncontroversial default, the way it was for the better part of a decade. None of this is to say that 8GB cards are suddenly useless, or that everyone with one needs to rush out and upgrade immediately. Plenty of games, especially esports titles, older releases, and less graphically demanding indie games, run perfectly well within that memory budget and will continue to for years. The point is narrower and more specific. For a growing subset of modern, graphically ambitious titles, particularly those using ray tracing, high-resolution texture packs, or aggressive open-world streaming, 8GB is increasingly becoming the limiting factor rather than the GPU's core compute performance. That distinction matters enormously when you are deciding what to buy, because it means the usual advice of matching a card's compute tier to your target resolution is no longer sufficient on its own. Memory capacity now deserves equal weight in that decision, not an afterthought squeezed in after comparing clock speeds and core counts. Looking ahead, there is little reason to expect this trend to reverse. Game worlds keep growing larger and more detailed. Ray tracing adoption keeps expanding rather than shrinking. Upscaling and frame generation technologies, despite their benefits, continue to add memory overhead rather than reduce it. Console hardware, which sets a meaningful baseline for what PC ports assume is available, is not going to shrink its memory pool in the next generation. Every one of these forces points in the same direction, toward higher memory requirements, not lower ones. An 8GB card bought today is likely to feel that pressure more acutely with each passing year, and the timeline for when it starts to feel genuinely constrained has been compressing faster than most predictions from just a few years ago anticipated. The broader lesson here extends beyond any single number stamped on a graphics card's spec sheet. It's a reminder that hardware requirements are not static, and the assumptions that felt safe at one point in a console generation or game engine's lifecycle can shift meaningfully within just a few years. What was a generous future-proof amount of memory in 2016 became merely adequate by 2020, and is now looking increasingly stretched heading into the back half of this decade. Buying hardware today means thinking not just about what runs well right now, but about the trajectory of what games will demand over the years you intend to keep that hardware. On that front, the evidence is fairly clear. 8GB VRAM is not dead yet, but it is dying faster than almost anyone in the industry expected, and anyone shopping for a new card should factor that trajectory into their decision rather than relying on assumptions that were accurate a few years ago, but no longer reflect where the industry is actually heading. Let's talk for a moment about what people who already own an 8GB card can actually do, because not everyone reading this is in a position to buy something new right now, and that is a completely fair reality. The good news is that most of the stutter and pop-in issues we have described are manageable through settings adjustments, even if they are not fully eliminated. Lowering texture quality by one notch, even on a card that otherwise handles a game's shading and lighting demands comfortably, frees up meaningful memory headroom and often removes the worst of the stuttering. Disabling ray tracing in titles where it is optional is another effective lever, since ray tracing's memory overhead is disproportionate to the visual benefit it provides on a memory-constrained card. Reducing texture pool size specifically, rather than dropping every graphic setting uniformly, tends to give the best return, because texture data is usually the single largest consumer of VRAM in modern titles. Some games also expose a dedicated VRAM usage indicator in their settings menu, and keeping an eye on that number while adjusting settings can help you find the sweet spot where usage stays comfortably under your card's ceiling without sacrificing more visual quality than necessary. It is also worth mentioning driver-level improvements, because GPU manufacturers have gotten noticeably better at memory management over the past several years. Techniques like more aggressive texture compression, smarter caching, and improved memory allocation algorithms have squeezed extra life out of 8GB cards that would have struggled even more under older driver revisions. This does not solve the underlying capacity problem, but it does mean an 8GB card today can often handle slightly more demanding settings than an 8GB card from 3 or 4 years ago could, purely because of software improvements sitting on top of the same hardware. That said, these gains are incremental and cannot indefinitely offset the growing appetite of new game releases, so treat them as a way to extend the useful life of existing hardware rather than a permanent fix. There is a useful analogy here to how storage capacity played out on smartphones a decade or so ago. 16 gigabytes of storage once felt entirely reasonable for a phone, right up until camera resolutions increased, app sizes ballooned, and suddenly that same 16 gigabytes felt cramped within just a couple of years, forcing people to constantly delete photos and apps just to install a routine update. VRAM on graphics cards is following a strikingly similar arc. A number that felt generous at launch is being squeezed by the steady, almost invisible growth of the software running on top of it, until one day, people look up and realize the specification they bought into is no longer matching the demands of the software ecosystem around it. The lesson from the smartphone storage saga is that these transitions tend to accelerate rather than plateau once they start, which is exactly the pattern we are now seeing play out with graphics card memory. For anyone building a new system or planning an upgrade in the near future, it is also worth looking specifically at how a given card's memory capacity compares not just to its immediate competitors, but to where the market segment as a whole is trending. A card that looks reasonably spec'd against today's lineup can quickly look undersized if the next generation broadly shifts its baseline upward, the way we saw happen when higher memory configurations became more standard at the upper end of the market. Checking recent reviews that specifically test VRAM-heavy scenarios, rather than relying solely on average frame rate charts, will give a far more accurate picture of how a card is likely to hold up 18 months or 2 years down the road, well after the initial round of launch day. Benchmarks have been published and largely forgotten. If you found this breakdown useful, consider looking closely at memory capacity the next time you compare graphics cards, not just clock speeds or core counts. It could be the difference between a card that ages gracefully and one that starts stuttering sooner than you expected. Do your own research before buying. Compare recent VRAM benchmarks rather than older reviews, and factor memory capacity into your decision with the same seriousness you give core performance figures. Thanks for watching, and I will see you in the next one.